To determine the derating factors for duct banks, specifically those with 2, 8, 10, or 14 ducts arranged in a maximum of 2 rows, you can utilize Figure B-310-2 Detail 3 from the National Electrical Code, or NEC. This figure is designed to provide derating factors for various duct bank configurations, accounting for the mutual heating effects between adjacent conduits. The arrangement of the ducts in your banks, where you have a maximum of 2 rows, results in each duct being adjacent to a maximum of 5 other ducts, including those diagonally positioned. Figure B-310-2 Detail 3 provides derating factors for duct banks containing 2, 3, 4, and 6 ducts in a row. Even though your specific duct banks may contain 8, 10, or 14 ducts, the crucial aspect is that each duct is adjacent to no more than 5 other ducts. Because of this geometrical constraint, you can conservatively apply the derating factors provided in Figure B-310-2 Detail 3. The key here is that the figure already accounts for the mutual heating between adjacent ducts and configurations with multiple rows. Applying these derating factors allows you to estimate the ampacity derating required for your conductors without resorting to complex Neher-McGrath calculations, which are more detailed and computationally intensive. The Neher-McGrath method is a more precise way to calculate the temperature rise and ampacity of conductors in underground duct banks, but it requires detailed information about the soil thermal resistivity, conductor characteristics, and installation conditions. Using Figure B-310-2 Detail 3 provides a simplified approach that is suitable for many common installations, especially when a conservative estimate is acceptable. Firstly, locate Figure B-310-2 in the NEC. Secondly, identify Detail 3 within the figure, which illustrates duct bank configurations. Thirdly, determine the number of ducts in your duct bank. Fourthly, ensure that the configuration of your duct bank does not exceed the maximum number of adjacent ducts considered in the figure, which in your case is 5. Fifthly, select the appropriate derating factor from the table based on the number of ducts and their arrangement. Sixthly, apply the derating factor to the ampacity of the conductors in your duct bank to determine their adjusted ampacity. The ampacity of a conductor is the maximum amount of electrical current it can carry continuously without exceeding its temperature rating. This rating is determined by the conductor's insulation type and the ambient temperature. The NEC provides ampacity tables for various conductor types and sizes. When conductors are installed in duct banks, their ampacity must be derated to account for the increased ambient temperature caused by the mutual heating of adjacent conductors. The derating factor is a multiplier that reduces the conductor's ampacity to compensate for this increased temperature. For example, if a conductor has an ampacity of 100 amps and the derating factor is 0.8, the adjusted ampacity is 80 amps. The NEC provides tables and figures that specify the derating factors for various duct bank configurations. These derating factors are based on the number of conductors in the duct bank, the spacing between the conductors, the depth of the duct bank, and the thermal resistivity of the surrounding soil. The Neher-McGrath method is a more precise way to calculate the temperature rise and ampacity of conductors in underground duct banks. This method takes into account the thermal properties of the soil, the conductors, and the duct bank. It also considers the heat generated by the conductors and the heat dissipated by the soil. The Neher-McGrath method is more complex than using the NEC tables and figures, but it can provide a more accurate assessment of the conductor's ampacity. The NEC requires that conductors be protected from overcurrent by fuses or circuit breakers. The size of the overcurrent protection device must be selected to protect the conductor from damage caused by excessive current flow. The NEC provides tables that specify the maximum overcurrent protection device size for various conductor types and sizes. When conductors are installed in duct banks, the size of the overcurrent protection device must be adjusted to account for the derated ampacity of the conductors. For example, if a conductor has an ampacity of 100 amps and the derating factor is 0.8, the adjusted ampacity is 80 amps. The overcurrent protection device must be sized to protect the conductor at its adjusted ampacity of 80 amps. The NEC also requires that conductors be identified by their color. The color of the conductor indicates its purpose in the electrical system. For example, black conductors are typically used for ungrounded or hot conductors, white conductors are typically used for grounded or neutral conductors, and green conductors are typically used for equipment grounding conductors. When conductors are installed in duct banks, they must be identified by their color. This helps to ensure that the conductors are properly connected and that the electrical system is safe. The NEC provides detailed requirements for the installation of conductors in duct banks. These requirements cover topics such as the spacing between conductors, the depth of the duct bank, the type of conduit used, and the grounding of the duct bank. Following these requirements helps to ensure that the duct bank is properly installed and that the electrical system is safe. Remember to consult the latest edition of the NEC for the most current and accurate information. Electrical codes and standards are updated regularly to reflect new technologies, materials, and safety practices. Always refer to the latest version of the NEC to ensure compliance with the applicable requirement. In summary, using Figure B-310-2 Detail 3 for duct banks with a maximum of 2 rows is a conservative and acceptable method for estimating derating factors. While the Neher-McGrath method offers greater precision, Figure B-310-2 provides a practical alternative for many common installations, especially when detailed soil and conductor information is unavailable. Always prioritize safety and accuracy by consulting the latest edition of the NEC and consulting with qualified electrical engineers when necessary. This approach simplifies the process of determining conductor ampacity in duct banks while ensuring compliance with electrical codes and standards. The NEC provides requirements for the installation of electrical equipment in hazardous locations. Hazardous locations are areas where there is a risk of fire or explosion due to the presence of flammable gases, vapors, or dusts. The NEC divides hazardous locations into different classes, divisions, and groups, depending on the type of hazard present. The NEC requires that electrical equipment installed in hazardous locations be specifically designed and approved for use in those locations. This equipment must be designed to prevent the ignition of flammable substances. The NEC also requires that electrical equipment in hazardous locations be properly installed and maintained. This includes ensuring that the equipment is properly grounded and that all connections are tight. The NEC provides requirements for the installation of electrical equipment in healthcare facilities. Healthcare facilities are areas where patients receive medical care. These facilities have unique electrical requirements to ensure the safety of patients and staff. The NEC requires that healthcare facilities have a reliable source of power to ensure that critical equipment continues to operate during a power outage. This may include having a backup generator or an uninterruptible power supply. The NEC also requires that healthcare facilities have isolated power systems in certain areas, such as operating rooms and intensive care units. Isolated power systems are designed to prevent electrical shock hazards to patients. The NEC provides requirements for the installation of electrical equipment in places of assembly. Places of assembly are areas where large numbers of people gather, such as theaters, auditoriums, and stadiums. These facilities have unique electrical requirements to ensure the safety of occupants. The NEC requires that places of assembly have adequate lighting to allow occupants to safely exit the building in an emergency. The NEC also requires that places of assembly have emergency power systems to provide power to essential equipment, such as lighting and fire alarm systems, during a power outage. The NEC provides requirements for the installation of electrical equipment in swimming pools and spas. Swimming pools and spas pose unique electrical hazards due to the presence of water. The NEC requires that all electrical equipment near swimming pools and spas be properly grounded to prevent electrical shock hazards. The NEC also requires that ground fault circuit interrupters, or GFCIs, be used to protect electrical circuits near swimming pools and spas. GFCIs are designed to detect small electrical leaks and to quickly disconnect the power to prevent electrical shock hazards. The NEC provides requirements for the installation of electrical equipment in agricultural buildings. Agricultural buildings, such as barns and poultry houses, have unique electrical requirements due to the presence of dust, moisture, and corrosive materials. The NEC requires that electrical equipment in agricultural buildings be designed to withstand these harsh conditions. The NEC also requires that agricultural buildings have adequate ventilation to prevent the buildup of flammable gases. The NEC provides requirements for the installation of electrical equipment in recreational vehicles, or RVs. RV are vehicles that are designed to be used as temporary living quarters. RV have unique electrical requirements because they are mobile and can be connected to different power sources. The NEC requires that RV have a properly sized electrical system to meet the needs of the occupants. The NEC also requires that RV have ground fault circuit interrupters, or GFCIs, to protect occupants from electrical shock hazards. The NEC provides requirements for the installation of electrical equipment in manufactured homes. Manufactured homes are homes that are built in a factory and then transported to the building site. Manufactured homes have unique electrical requirements because they are built in a different environment than traditional site-built homes. The NEC requires that manufactured homes have a properly sized electrical system to meet the needs of the occupants. The NEC also requires that manufactured homes have arc fault circuit interrupters, or RSIs, to protect occupants from electrical fires. RSIs are designed to detect small electrical arcs and to quickly disconnect the power to prevent fires. The NEC provides requirements for the installation of electrical equipment in floating buildings. Floating buildings are buildings that are designed to float on water. Floating buildings have unique electrical requirements because they are subject to movement and moisture. The NEC requires that floating buildings have a properly sized electrical system to meet the needs of the occupants. The NEC also requires that floating buildings have ground fault circuit interrupters, or GFCIs, to protect occupants from electrical shock hazards. Remember that the NEC is a comprehensive document, and it is important to consult the specific requirements that apply to your particular installation. Always consult with a qualified electrical engineer or electrician to ensure that your electrical system is installed in accordance with the NEC and other applicable codes and standards. By following the NEC and other applicable codes and standards, you can help to ensure that your electrical system is safe and reliable.